Okay, it's 9:30, so I'm going to go ahead and get started. So good morning, everyone. Welcome to a special edition of our usual lecture time. First off, I want to, say I'm sorry that, I had to do this. Of course, normally I think what would be best was to, to have these lectures during our normal time, because that's the time that everyone's kind of blocked off during their week in order to have the lectures. And doing these live is a lot better than than doing it kind of asynchronously like this, because usually you guys get to ask questions, and that adds a lot to the experience of the lecture. So I know this isn't ideal, but because of technical difficulties and my internet conking out for a few hours last night, and this is something that I wanted to do just so that we don't kind of fall behind, because I want to make sure that we get through this so that we can start turbulence next week. Just so, we kind of stay on track. So again, I know this isn't ideal, and I know many of you are going to be watching this on YouTube. I see Uriel joined in, so that's good. So at least I have one person watching, better than my last lecture where I was just talking to myself for, 45 minutes. So this is nice. But, hopefully, the internet stays stable. I saw the Spectrum repair guy yesterday, so hopefully he fixed things and made things stable for the next couple weeks, because that's what we're going to need the internet for. Okay. So I wanted to make one announcement that I didn't get to make yesterday. Some of you may have noticed already that homework 6 is posted. So homework 6 is going to have problems and questions about what we're covering this week on fluid instabilities. And also what we're going to be covering for the rest of the semester based on turbulence. Okay, so it's going to be due not on the last day of class, but it's going to be due on that Friday. It's going to be due. So today's Thursday of week 14. So it's going to be due Friday of week 16. So you guys are going to have 2 weeks to do it. So probably when you look at it right now, there's not much you can do because we still need to cover instabilities and turbulence. So that's why I wanted to give you a couple extra days at the tail end, just to make sure that you guys have enough time to work it out. Okay. So go ahead and check that out when you get the chance, and then I'm going to go ahead and get started. Okay. Okay. So where we left off, I think it's been a while since we've had a lecture, because on Monday we had the midterms. We didn't have a lecture that day, and then last time I saw you guys was last Wednesday. So last time when we left off, we were covering fluid instabilities. So we just finished talking about the Kelvin-Helmholtz instability, which is probably one of the most famous fluid instabilities out there. So the direction that I want to go today is I wanted to kind of talk about kind of more general methods to analyze instabilities. And unfortunately, due to kind of the complexity of the equations, we won't be able to solve a lot of these analytically. But we can talk about some just kind of heuristics and just some kind of general processes that we can follow. So our starting point is we're going to talk about what's called the ORrSommerfeld equation. Okay. So the ORrSommerfeld equation, it's a basically the way that we're going to do it is we're going to apply kind of our method of normal modes to our conservation of momentum equation. Basically, we're going to apply directly to Navier-Stokes. Because you remember from last time when we did Kelvin-Helmholtz, we kind of applied the normal modes method to kind of a specialized case that was based on the geometry and the situation that we were in. So while that works great for Kelvin-Helmholtz, the equations that we actually got weren't exactly due to conservation of momentum. They were more due to kind of the boundary conditions that we were imposing on the situation. Okay? So the ORrSommerfeld is going to be a bit more general, but because of that, it's going to be a lot more difficult to solve. Okay, but kind of the main thing that this is going to allow us to do is that this is going to allow us to see how viscosity kind of factors into instability. Because the Kelvin-Helmholtz instability, while it's really cool, it was totally inviscid. So viscosity didn't factor into that at all. So the ORrSommerfeld equation, because it's more general, it's going to allow us to see how viscosity factors in. Okay, and it's going to kind of be the launching point for it's kind of the transition point between kind of what we did before and turbulence, because what we'll be able to see is that from the ORrSommerfeld, or just from the ideas kind of motivated in the ORrSommerfeld equation, we will be able to see how viscosity can actually be a destabilizing agent within fluid flows. Because normally what we expect is that viscosity is actually going to help stabilize our fluid flows, just because of its nature. But actually, viscosity can actually destabilize fluid flows, and that's going to lead kind of directly into our discussion on turbulence. Okay. So before we start, let's just talk about some assumptions that we're going to do. So similar to what we did in Kelvin-Helmholtz, what we're going to assume is that we're going to assume our velocity is only in one direction. Okay. So our velocity components, at least in our base case, only has one direction. Okay. And our dependence and the dependence of the velocity is only going to be on one spatial variable. Okay. So kind of one example of this would be kind of our flow in a pipe, okay, where we know if we have kind of pressure-driven flow within a channel or a pipe, we have a velocity distribution that looks like this. And then our U is only in one direction, so it's going to be kind of along the pipe, and it only depends on one variable, which is Y. Okay. And then just like we did before, we're going to assume steady state. Okay. So we're not going to have any time derivatives. Okay. And then this will kind of be the launching point for us to use our method in normal modes. Okay. All right. So do you have any questions? Okay. We're good. Thanks. We as in just you. Okay. So let's go ahead and apply our method in normal modes. So remember, our method in normal modes, the way that we do this is we're going to add a perturbation to our flow field. Okay. And so what that looks like is that if we take the total velocity vector, it's going to be a sum of both our base case and our perturbations. So I'm going to use the same notation that I used before, where I use capital letters to denote kind of our base flow that's in the background, and our perturbations, I'll give it the lowercase letters. Okay. So we can have a perturbation in the x velocity, and we can also have perturbations in the y and the z direction. So we have little u, little v, little w. Okay. So even though our base case is only one direction, our perturbations can be in kind of any direction. Okay. And then since we're doing this off the general Navier-Stokes, we also have to add a little bit of perturbation for the pressure. So our pressure total is going to be a sum of P, big P here, which is our base pressure, plus the little perturbations of pressure. Okay? And so what we can do is we can plug this into our momentum equation. Okay. So let's go ahead and do that. Okay. So basically what I'm doing is I'm just plugging in those velocity components into our momentum. So even though our base case was steady, you can see here that I still have an unsteady term for the perturbations because we haven't made any assumptions on that yet. Okay. Okay, and then to kind of write the viscosity term in shorthand, I'm going to have it be 1 over the Reynolds number times the Laplacian of u plus u. Okay. Okay. And so from here, we have a lot of terms. What we can do is we can distribute. So I don't think this is going to fit on this page, but I can at least start it. Okay. Okay. So the let's see. Oh, I need one more. Let's see. Oh, I need u du dx. Okay. So you can see, when we have these kind of quadratic terms, they kind of expand out to quite a few terms. Okay. Sorry, there was a little yapping dog that just ran past my window. Or I think it's a small child. I can't tell. Okay. So these are all the convection terms. So I'll do the other terms on the other side. Okay. So after we kind of distribute the terms, we end up with stuff like this. Okay. And so what I'm going to do is I'm going to start canceling some of these terms. Okay. Okay. I need to cancel this guy too. Okay. So the reason I'm canceling these terms is that we're going to assume a few things. So first of all, we're going to assume that, this is something that we've already assumed, is that we assume that our base flow, big U, only depends on Y. So whenever we see any derivatives of the base flow with respect to X or with respect to Z, let me cancel this guy too, then we can go ahead and cancel those terms. Okay. So basically, any derivative of big U with respect to Y and Z, we're going to cancel out because we assume that our flow is only one-dimensional. Okay. And then the other thing we're going to assume is that anytime we have a product of perturbation terms, we have little u times d little u dx, or little u times, little v times little d little u dy. So anytime we have kind of two little letters kind of multiplied with each other, we're going to cancel those out because what we're assuming is that, that's basically be a product of two perturbations, and we're assuming that the perturbations are small. So the product of two small things is going to be something that's even smaller. So we're going to assume that relative to other terms in the equation, those terms are going to cancel out. Okay? So then all we're left with is the time derivative term for the perturbations and two convection terms that involve those things. Okay. All right. Any questions on this? Okay. Okay, so that's all the convection terms. So then now let's fill in the other side. So the other side's pretty simple, and we're actually not going to cancel anything. So first we have our pressure term. Okay. So we have two pressure terms, one for the base pressure and one for the perturbation pressure. Okay. And then we have two viscosity terms that kind of come out like that. So there's no kind of foiling or no distributing for that at all. Okay. So that's kind of what we get just by directly plugging all of those in. So I'm going to make one more assumption. Not really an assumption. This is kind of based off things we already know. Okay. So we know that kind of before we plugged in all these perturbations. Oh yeah. So we canceled the W DUZ du dz term. So this term right here. Okay. So the reason we canceled that term is because big U is only a function of y, right? So you can see right here that U is only a function of y. So when we take the derivative of big U by z, then that term goes to 0 because big U does not depend on z at all. Okay. So little u we don't know yet. So little u is a perturbation that that can depend on all those. It can depend on everything. So the only thing that we know is the base flow. So the little u's, the only thing that we know is that if we multiply two little u's together, or little u times a little v, then those will cancel out because those are the product of two kind of small things. But besides that, we're not making any other assumptions on the little variables. Right, exactly. Yeah, we just cancel it just because they're small. Mm-hmm. Okay. So we already know that the base flow already satisfies a conservation of momentum. So we know that kind of before adding any perturbations, then we know the base flow satisfies this equation. Okay. Okay. So we already know, kind of before we plugged in our perturbations, that our base flow is going to satisfy this. And so what we can do is we can use this to cancel out things in our previous equation. Okay? So our previous equation right now consists of these guys and then all the terms on the previous page. So there's still a lot going on there. But since we already know that the base flow satisfies its own momentum, we can go ahead and take this term and this term. And we know that when we add them together, they get 0 because they already satisfy their own momentum. So what we can do is we can cancel those from the equation, and then we end up with something a little bit simple. Okay. Right. So in the end, we get, after applying those cancellations and bringing in the convection terms from the previous page, we get du d little u dt plus big U times d little u dx plus v times d big U dy is equal to minus the gradient of the perturbation pressure plus 1 over the Reynolds number times gradient, Laplacian of little u. Okay. Okay. So this is the equation that results from when you apply basically our perturbations to the x momentum. So we can do the same things for the y and the z momentum. Okay, and we get basically very similar expressions. Oh, let me put it in this form. So we have minus dp hat dy plus 1 over the Reynolds number, d Laplacian of v, and we have dw dt plus u dw dx is equal to minus p hat dz plus 1 over the Reynolds number Laplacian of w. Okay. Right. So we have three equations here that we can solve for our perturbation velocities. Okay. Right. And then just like we did for the Kelvin-Helmholtz, we can plug in a basically a Fourier representation of u, v, and w. Okay. MP hat. Okay. Because remember, that was our method in normal modes, where we assumed that our perturbations were sinusoidal in nature. And then if we do that, then we can solve for the growth rate of the perturbation. It was either sigma or it was our wave speed c. Okay. So in the notes I have the equations for this, but it's actually not going to be useful because, as you can imagine, we have these four. And conservation of mass too. We have these four partial differential equations to solve for these perturbations, where the perturbations can depend on x, y, z, and t. So this is an extremely difficult problem, which which you can solve probably numerically, but by hand, it's not something that's going to be useful for us. Okay? So what we're going to do is we're going to apply some more assumptions to this and get this down to a form that we can use. Okay. Okay. Any questions on this? Okay. Okay, so let's apply some more assumptions to basically simplify this problem, and they're not totally unreasonable assumptions either. So let's apply an assumption known as Squire's theorem. So I don't know the history behind this theorem, so I don't know if it's someone actually named Squire, or if it was a knight in training that somehow was really good in fluid mechanics, and he came up with this theorem. But basically, what he says that when you have when you're considering stability of a 3D problem, which is what we have right now, because since we have disturbances in both u, v, and w, what he determined, and the proof of this is in the book, or you can easily find this online, is that if you took a 2D problem that has kind of the same dimensions as the 3D one, the 2D one is just inherently more unstable. Okay, so what he basically says is for every 3D unstable problem or instability problem, there exists a more unstable 2D problem. Okay. So that's nice because right now we have a 3D problem, which is really difficult just because there's a lot more unknown, or there's a ton of unknowns. But by using Squire's theorem, what we can say is that let's just disregard the third dimension and let's just consider a 2D problem because that's going to be more unstable. So in other words, what we're going to do is we're going to basically ignore, or we're going to use Squire's theorem to ignore the z component. Okay? So we're basically just going to consider the flow in x and y. Okay? And so by doing that, this helps us out quite a bit because since now that we have 2D flow, we can make use of a friend that we've used quite a lot in this class, is that when you have a 2D flow, instead of solving for both the x and the y components of velocity, so instead of solving for u and v, what we can do is we can solve for what's called a stream function. So remember, the stream function is a scalar variable phi, or psi, sorry. And then once we know psi, we can actually solve for the velocity components. Okay. My iPad will cooperate with me. Okay. So we can say that u is equal to d psi dy, and then v is equal to minus d psi dx. Okay. And so this helps us out quite a bit more, because then this makes it so that we only have to solve for just psi instead of just u and v. Okay. So basically, you know, the point of all these assumptions is to make it so that we can reduce the number of variables that we solve for, because, you know, every time we kind of reduce the number of variables that we solve for, our problem becomes that exponentially easier. Okay. And so now that we have things in terms of psi, so now this is, if you kind of recall from Kelvin-Helmholtz, that's kind of what we did too. So for Kelvin-Helmholtz, we put things in terms of a scalar function. So when we do that, when we introduce disturbances, we can introduce the disturbance as kind of a perturbation stream function. Okay. And so this is kind of the function that we'll plug in. Okay. So we'll say that our perturbation stream function is going to be the magnitude of the disturbance. Okay, so our magnitude of the disturbance, remember, depends on the same, it has the same functional dependence as our base flow. Okay, so since our base flow is only a function of y, then the magnitude of our disturbance is also going to depend on y. Okay. And then we're going to do an exponential of ik of x minus ct. Okay. Well, remember, k right here is the wave number of the disturbance, so that determines kind of the spatial frequency of our disturbance, and then c, this is our wave speed. Okay, and so since this c is in front of the t, in front of time, c is kind of what we're ultimately most interested in, because that's going to tell us whether our situation is going to be stable or unstable. Okay. Okay, so then what we can do is we can plug this stream function into our momentum equations and conservation of mass, and then we can finally arrive at the ORrSommerfeld equation. Okay. Are there any questions on this before I turn the page? Okay. Okay. You know, when you actually go and plug it in and work it out, it's a lot of algebra. That I think is you know, not as useful for the class. So I'm just going to give you the final result. Okay. So the final result is u minus c. Okay. Remember, big U here, that's our base flow, and c is our wave speed. Okay. Then we have d squared psi hat dy squared. Okay. Minus k squared psi hat. Okay. Minus psi hat times d squared u dy squared, okay, is equal to 1 over ikre. Okay. So this is our viscous term, and then we have d to the 4th psi hat over dy to the 4th minus 2k squared d squared phi hat dy squared plus k to the 4th psi hat. Okay. So this equation that I've boxed right here, this is the ORrSommerfeld equation. Okay. So of course, you know, this is a 4th order differential equation, so you need to have lots of boundary conditions on psi. Okay. And even though it's a ordinary differential equation and it's linear, which are you know, both very good things, you can see that this is very difficult to solve in practice. So Many people, no one really solves this by hand anymore. Usually what people do is that they solve this using a computer. Okay. So even though we're not going to actually solve this equation in this class, I think it's important to kind of know where it came from, and just to just so you kind of know how we're going to use it going forward. Yeah. So next to IK, this right here is Reynolds number. Let me make this bit more neat. Yeah. Mm-hmm. Yeah. So this kind of last term in parentheses here, that came from the viscous term. So that's a 1 over the Reynolds number right there. Okay. And so what we're going to do first is that now that we have this nice equation, we're going to consider some kind of limiting cases of this. So first thing we're going to do is we're going to assume that the flow is inviscid. So we're going to let the Reynolds number go to infinity. Okay. And then we're going to see what results from the equation and what kind of and what conclusions that we can draw from it that are actually going to be useful for calculations. Okay. Okay. Any questions on this? Okay. Okay. So if we let Reynolds number go to infinity, then this basically this is basically going to give us an inviscid situation. So there's no viscosity. Okay. So this is inviscid stability of parallel flows. Okay. So by making that assumption of letting Reynolds number go to infinity, that simplifies our ORrSommerfeld equation, because then we have U minus C times d squared psi dy squared minus k squared psi minus psi times d squared u dy squared. Okay. Right. And so when you apply that assumption, this equation, or the form of this equation, has a special name. So this is called the Rayleigh equation. Okay. So since we don't have viscosity anymore, then what's going to happen is that the flow that follows this equation is going to slip at any solid boundary. So because we don't have viscosity, there's no way we can apply no slip, but that's okay. Okay. So if you've taken a kind of advanced mathematics class, you know that when you look at this equation, and what you should see is that this basically forms an eigenvalue problem. So this isn't a math class, although sometimes it can feel that way, I know. But we're not going to actually solve this eigenvalue problem. But if you kind of just know what those are and what we're solving for, then that can help you kind of understand what's going on. Okay? So whenever you have an eigenvalue problem, you're solving for kind of two things simultaneously. So you're solving for the eigenvalue. Okay? So it's kind of important to define what that is for this problem. So the eigenvalue for this problem is actually going to be the wave speed. Okay. Okay. Which is good because C is kind of what we're interested in, because depending on the behavior of C, that's going to tell us about the stability of the situation. Okay. And then the disturbance psi, that's going to be our eigenfunction. Okay. So these are a pair. So whenever you're solving eigenvalue problems, you're kind of solving for both, because these things are paired where a certain eigenfunction psi is only going to be a solution for its corresponding eigenvalues. Okay? But that's kind of just the mathematical background, because all we're interested in is just C. Okay, that's all we kind of care about. Right? So because of the nature of the solution of eigenvalue problems, whenever you find a solution for C, where C can be a complex number, okay? Okay. And so if you find a solution to the eigenvalue problem for some complex number C, then just by the properties of the eigenvalue problem, its complex conjugate will also be a solution. Okay. Okay. So that means if we have C, which is equal to C real plus I, Ci is a solution, then C is equal to C real minus I, Ci is also a solution to this problem. Okay. So if you recall, kind of when we were discussing kind of the wave speed form of the normal modes method, then we know that whenever we get a wave speed with a positive imaginary component, so whenever we get something like this, okay, where kind of the focus is on this guy right here, where the imaginary part of your wave speed is positive, then we know that we have an unstable solution. Okay. And so because we were kind of, we reduced to an eigenvalue problem, we know that whenever we have any kind of complex solution, even when when the imaginary part is negative, because the complex conjugate will also be a solution, we know that anytime our wave speed has any kind of imaginary component, then we're going to be unstable. Okay? And so the only way for you to get stability for an inviscid problem is if the imaginary part of the wave speed is 0. Okay. Okay. Any questions on this? Okay. So let me just kind of write down what I just said. So only way okay. So the only way that we get a stable solution is if our imaginary part is equal to 0. Okay. But this is only for inviscid flows. Okay. So if you can solve the eigenvalue problem and you get your solution for the wave speed, and you get the imaginary part equal to 0, then that's the only way for this to be stable. Okay. Okay. But all of that is kind of very abstract math stuff. So what are some kind of things that you can actually use in practice, or things that we can actually use for problems in this class, kind of more specifically. Okay. So I want to talk about kind of two important results that come from the Reynolds equation. Okay. So the first is Reynolds. It's another kind of criteria, and it's named after Reynolds. So the first is Reynolds inflection point criteria. Okay. And so this kind of goes back to when we were talking about turbulent boundary layers and separation. Okay. And so what Rayleigh's inflection point criteria states that what it says that in order for there to be you know, an unstable flow, what he says was that a necessary but not sufficient condition was that there has to be an inflection point somewhere in the flow. Okay. Okay. So an inflection point basically says that you know, the second derivative of the velocity has to equal 0 somewhere. Okay. So if you have d squared u dy squared equals 0 somewhere, then Rayleigh's inflection point criteria is satisfied, and it's possible to get instability there. Okay. So the kind of the key words here in this criteria is necessary but not sufficient. So you know, just because you have an inflection point in your flow doesn't mean that it's that it can be unstable, but it is kind of a first requirement. So if your velocity profile does not have any inflection point, then what Rayleigh's criteria says that there's at least, you know, without viscosity, there's no way for it to turn unstable. Okay. But the opposite isn't true. So just because you have an inflection point doesn't mean you're unstable. But if you have no inflection point, then you're definitely going to be stable. Okay. So that's useful a little bit, but it's, you know, not as useful because there's actually a lot of flows out there that have an inflection point, but are still very stable. So later on, this was Rayleigh's inflection point criteria was improved upon. And it was improved upon by a researcher named Fjortoft. So this is Fjortoft's theorem. My stylus is kind of freaking out on me. Okay. So this is Fjortoft's theorem. Okay. And so what Fjortoft found was that there's a stronger criteria for to determine stability. Okay. And his condition is like this. So we have u minus ui times d squared u dy squared is less than 0. Okay. And so what this ui right here, this is the velocity at the inflection point. Okay. So it's kind of like an addendum to Rayleigh's inflection point criteria. So what Fjortoft says is that you know, he agrees that there has to be an inflection point in the flow in order for it to be unstable. But if you compute this quantity right here of u, which is the velocity anywhere, minus the velocity at the inflection point, and you multiply that by the second derivative of u, and if that quantity is less than 0, then this flow that's a stronger condition for there to be instability. Okay. Okay. So this ui is the velocity at the inflection point, and this u and this d squared u dy squared, this is the velocity anywhere. So if you measure this quantity and you find that to be less than 0 at some point, then that's a strong indication that you're going to be unstable. Okay. Any questions on this? Okay. Okay, so using Fjortoft's theorem, we can come up with a kind of a general list of flows that are generally stable and flows that are generally unstable. Okay. So this is generally. Okay. So generally, flows that are stable are flows like Couette flow, Poiseuille flow, and boundary layers with a favorable pressure gradient. Okay. So if the flow kind of fits into one of those categories, and it's generally going to be stable. Okay. So we can come up with a list of flows that are generally unstable using this criteria. So this would be jets, wakes, okay, shear layers, and boundary layers with an adverse pressure gradient. Okay. So if your flow kind of falls into these categories, then it's generally going to be unstable. Okay. Okay. So that's all the theory for inviscous stability. So now what about viscous flow? So that's that's kind of the theme of this class. So kind of like what I led off this section with is that generally viscosity is going to be something that stabilizes your flow because viscosity tends to dampen out any kind of sharp gradients, and because of that it tends to take these perturbations and kind of suppresses them. So generally viscosity can be stabilizing, but there are some cases where it can be destabilizing, and that kind of leads us into turbulence. Okay. And so just some examples of this is that, we already know that, when we studied boundary layers, we already know that once the Reynolds number exceeds a certain amount, like especially for the Blasius boundary layer, for instance, then our situation is going to become unstable. Okay? So the reason this happens is because viscosity actually can contribute to instability. Okay? And just in a nutshell, the way that viscosity does that is that it provides a mechanism, or provides a form for these perturbations to kind of steal energy from the base flow. Guys, remember, viscosity is a lot of things, but the main thing that that viscosity is, what it does for fluids. When we talked about unsteady laminar flow, is that viscosity is an agent to basically to diffuse momentum or to transfer momentum. Okay, and so what tends to happen is that viscosity can take the momentum or take the energy from the mean flow and then transfer that into these perturbations. And then as these perturbations get more energy, then that's what causes them to grow and become unstable. Okay, so let's see how that actually works out. Okay, and so I'm going to write an equation here. I'm not going to derive it, but it's it's not too difficult to understand. So what it is basically, it's a control volume expression, which expresses the rate of change of energy or kinetic energy of the disturbances. Okay, so that equation looks like this. So we have ddt of integral of 1/2 u squared plus v squared, right, dv. So this is a control volume analysis, so we're integrating over a volume, okay, minus little u, little v, times du dy dv minus nu viscosity of gradient of u squared dv. Okay. Okay, so let me label these terms. So then this term is term 1. We'll call this one term 2. We'll call this one term 3. Okay. So term 1, because we have the ddt on the outside, this is the total rate of change of disturbance kinetic energy. Okay. And so ideally, for a stable solution, that quantity, that total rate of change of the kinetic energy should be negative. Because if that change is negative, that means that the perturbations are losing energy over time, and thus they're going to eventually go away. So then that's what we have in a steady situation. Okay? But for an unsteady or unstable situation, then that quantity on the left is going to be positive. Because if that's positive, then we know that the perturbations are gaining energy over time, and as they get more energetic, then they become bigger and bigger, and they lead to really unstable solutions in your flow. Okay. Okay. So the second term, this is work done by the perturbations. Okay. Or work done by UV against the mean shear. Okay. And then finally, we have 3. For 3, this is the viscous dissipation of kinetic energy. Okay. And so basically what that third term represents is kind of a conversion of the kinetic energy of the flow, where there should be a little u, sorry. It's a conversion of the kinetic energy of the disturbances into heat, right? So just like friction in solid mechanics, viscosity has the same effect, where it can take these small disturbances and basically just dissipate them into heat. So that's basically energy lost by the perturbations just due to heat. Okay. So you can see right here that on the left-hand side where we have our total rate of change, and on the right-hand side we have two integrals with a minus sign out front. Okay. So as long as these integral quantities that I've underlined here, as long as those are positive, then the minus sign out in front will basically ensure that this entire thing will be negative, which is what we want, because we want the disturbances to go down over time. Okay. So are there any situations that cause kind of a disturbance in the force, or kind of any kind of mess up of this balance? And that answer is yes. And the way that this can get messed up is actually due to viscosity. Okay. All right. Before I turn the page, are there any questions on this? Okay. Okay. So due to viscosity, we have something that's that can be interesting. Okay. Okay. So due to viscosity, this term right here, U times V, which is the product of two disturbances, this can actually be negative. Okay. And so because this can be negative, what can happen is that you have a positive integral on the right-hand side and a negative integral. And if that effect of the positive integral is bigger than the negative one, then this is going to lead to a positive growth of kinetic energy. Right, so if integral 2 on the previous page overwhelms integral 3, okay, then what happens is that it results in a net increase or net rate of increase of kinetic energy. Okay. And so if we have a net increase of kinetic energy, then we know that the perturbation is going to grow over time, and then we're going to get an unstable situation. Okay? So the product of these two disturbances, they actually have a special name, which we're going to go over a lot next week. So these are actually called the Reynolds stresses. Okay. So the Reynolds stress is basically just a product of two, perturbations, random perturbations. They can kind of go in any direction. Okay? And then due to viscosity, what can happen is that the Reynolds stresses, what they can do is that they can actually steal energy from the base flow. Okay? Okay. And then the mechanism that allows it to basically steal that energy is viscosity. Okay. Because viscosity, remember, it provides a way for momentum to kind of be transferred, within the fluid. Okay. So if viscosity can transfer momentum for the base flow, it can also transfer energy and momentum from the base flow to the disturbances. Okay. And then if this happens enough, then the disturbances will grow in energy, and then they'll start to become really unstable. Okay. So in particular, it's the action or the interaction between shear, which is big du dy, okay, or this guy right here, okay, It's the interaction between big du dy and the Reynolds stresses that will produce kind of this effect of the disturbances stealing energy. Okay, and so if you remember, viscosity is kind of the main thing that causes our velocity gradients to be pretty high, right? So that's kind of another thing. So velocity gradients, or velocity gradients result from viscosity being present in the fluid. And because we have velocity gradients, that provides a mechanism for these disturbances to kind of steal energy from the mean flow. Okay? And when that happens, then these disturbances will grow in time, and then eventually the flow will become unstable. Okay. All right. So this phenomenon of these kind of small disturbances stealing energy from kind of the base flow or the main flow, this is known as the energy cascade. Okay. And so I kind of just want to introduce the term now, because this is something we'll be talking a lot next week in turbulence. But kind of think of that, kind of remember this phenomenon of kind of small flow structure or small perturbations stealing energy from the main flow through viscosity. Okay, and then that's going to be called energy cascade, and it's kind of one of the central ideas behind turbulent flow. Okay, any questions on this? Okay. Okay, so the last idea or the last concept that I just want to touch on for instability is is boundary layer stability. Okay. So it's kind of been hinted at up to this point, but we know that a boundary layer, when we talk about instability of a boundary layer, what we're actually talking about is separation. Okay, so we know that if a boundary layer separates, then that's basically a result of an instability happening in the flow and that growing with respect to time. Okay, so boundary layer stability and separation are kind of two sides of the same coin. They're just kind of two different ways that you can talk about it, two different ways that you can analyze it, but the result is the same. You have a boundary layer that separates and it becomes chaotic, and you have a wake, and usually most of the time that's a bad thing. Okay? So when we talked about boundary layer separation, we talked about kind of two situations. So we talked about cases where we have a favorable pressure gradient. And then we contrasted that with cases where our pressure gradient was adverse. Okay. So a favorable pressure gradient, remember, that's when pressure is decreasing in the direction of flow, and adverse is when the pressure is increasing in the direction of flow. So oftentimes the stability of boundary layers, you'll see these kind of curves in the literature when you see reports of like boundary layer stability over an airfoil or any kind of geometry. You'll see them often summarized in what's called a neutral curve, or sometimes they're called thumb curves because they look like thumbs. Okay, and so they look something like this. So let me draw the curve for an adverse pressure gradient first, and then I'll kind of explain the different features of the curve, and then I'll overlay the curve for a favorable. Actually, let me just draw two separate curves, because I think with both of them on there at the same time, it gets a bit confusing. Okay. So these curves, the x-axis is has the Reynolds number. So on the y-axis, we have this quantity k delta. Okay, where delta, remember, that's the thickness of the boundary layer, and k is the wave number of the disturbance. or in other words, the kind of the spatial frequency of the disturbance. Okay. So it looks something like this. So it really looks like you put your thumb and you kind of pushed it onto the paper. Okay. 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 So let me draw out the regions. Okay. And so the way to interpret this thumb curve is kind of the first thing I want to draw your attention to is this guy right here. Okay. And you notice like the curve with the x-axis defined as the Reynolds number, kind of the leftmost part of the curve, kind of where it sticks out the most on the left. If you kind of draw a vertical line down to the x-axis, that's going to be your critical Reynolds numbers. Remember, the critical Reynolds number, this is the Reynolds number where turbulence or instabilities or separation, this is when things start to occur. Okay. Okay. And you'll notice that it only occurs for a certain for a disturbance of a certain frequency, right? So it's, you know, this disturbance is only going to occur for a k delta value that's, you know, that's kind of intersecting at that axis there. Okay. Because at this Reynolds number, you know, if you have a value of k delta that's either up here or down here, you're not going to get a disturbance. So what this tells you is that the kind of the first disturbances that occur in a boundary layer, they occur at a very specific spatial frequency, or, you know, the spatial frequency together with the thickness of the boundary layer. Okay. Okay. And also what this tells you is that when you have any Reynolds number below the critical, then you're going to have a stable boundary layer, so you're not going to have separation. Okay. So this is for adverse only. Sorry, I should have labeled this. Yeah, so the favorable pressure gradient one looks a little bit different, so I'm going to draw that on the next page. So normally these curves are overlaid, but I think it's super confusing when they're overlaid, so I'm just going to draw them as two separate curves. Yeah. Okay. So if you have any combination of Reynolds number and k delta, and you're inside the thumb curve, then what's going to happen is that your boundary layer is going to be unstable. So it's going to be either going to turn turbulent or it's going to separate very quickly. But if you have any product of these that's outside the curve, then you're going to be stable. Okay. Okay. So besides that, the other thing I want to draw your attention to is kind of this area of the curve right here. Okay. So you can see that once our Reynolds number gets really, really high, then we kind of have this area of the curve that kind of flattens out. So I didn't draw it that well, but it should kind of flatten out like this. Okay. So what this tells you is that at high enough Reynolds number, you're always going to have some kind of instability in the flow. Okay. And the reason for this is that because when you have an adverse pressure gradient, then we know that there's going to be some inflection point in the flow. Okay. And when we, you know, and what we talked about earlier is that you know, whenever you have an inflection point, that's kind of a good indication that you might go unstable. Okay, particularly for this case where Reynolds number gets really high, because we know that when Reynolds number gets really high, then the viscous effects get really low. Okay, so it's mostly going to be inertial effects that are dominating. And we saw that, you know, those two criteria that we went over, the Rayleigh's inflection point criteria and the Fjordhoff's theorem, those were strictly for inviscid flows. Right? So inviscid flows have Reynolds number that's really high. So this is kind of consistent with those theorems where if you have inviscid flow and you have an inflection point, then it's very likely you're going to have instabilities that grow over time. Okay. Any questions on this? Yes, I mean it starts laminar, but as you increase the Reynolds number and as things get unstable, then you become turbulent. Mhm. So it's kind of for both laminar and turbulent, depending on the characteristic of the flow. Mhm. Okay, so that's for adverse pressure gradients. So then now let's draw the curve for a favorable one. Okay. Okay, so our axes are the same. So we have Reynolds number on the x-axis and a K delta on the y-axis. So for a favorable pressure gradient, it'll look like this. Okay. Okay. So we have a much lower unstable region because the favorable pressure gradient tends to keep things it tends to keep things pretty tight, so this instabilities won't grow. And then just like we saw for the adverse, we also have a critical Reynolds number. Okay. And the thing is, if you have a favorable pressure gradient, then the critical Reynolds number, which triggers instability, will be higher. Okay. Because the favorable pressure gradient, what it's going to do, it's going to kind of help you keep the boundary layer attached and keep it laminar. Okay. So you can't really see it, and I kind of tried to draw it kind of on the right here, is that when you have a favorable pressure gradient, it tends to take your curve for the adverse one and kind of pushes it to the right and kind of smushes it down just like that. Okay. Okay. And so the other thing I want to draw your attention to is the behavior at high Reynolds number. Okay. So for the adverse pressure gradient, we saw that if your Reynolds number is high enough, then you're always going to get instability. That's because the adverse pressure gradient will cause an inflection point in your flow. But if you have a favorable pressure gradient, then that kind of prevents inflection points from happening. So actually, if you have a favorable pressure gradient and your Reynolds number is high enough, then that's actually going to keep your boundary layer attached. Okay. So this is a fact that that aerospace engineers they use to design their wings, so that they try to design their wings such that if they're in this regime of Reynolds number that are high enough and they have a favorable pressure gradient, then they don't have to worry so much about the boundary layer separating, because having your boundary layer separate over something like an airfoil is really dangerous, because that's what causes stall, and that's what causes airplanes to basically fall out of the sky. Okay. So any final questions on this? Right. So the question is, for the case of zero pressure gradient, would that be considered adverse or favorable? So for so these curves are, I just kind of gave you two examples for these but depending on how adverse or how favorable, these curves can definitely move. So it's not like it's not like a switch where it turns from an adverse pressure gradient from this one to a favorable like this one. So there's definitely degrees. So depending on how favorable and how adverse they are, these curves can either grow or shrink according to that. And a lot of times these curves are obtained through experimental measurements. So if you have kind of a zero pressure gradient, what can result is probably something that's kind of in between the two that I have right there. Yeah. And then if you have a pressure gradient that's more favorable, that's going to shrink this even more. A more adverse will make it grow even more. All right. Any more questions on this stuff? Okay. So that's it. So that's all I got for instability. So when we pick this up on Monday, we'll be covering turbulence. So thank you, Uriel, again for tuning into this special edition, and thank you everyone who's going to be watching this on YouTube. So I know that this wasn't ideal. I definitely don't prefer this, especially because it's in the morning, and I know a lot of you guys are working or you have your other classes you attend to. So I apologize again for the inconveniences this caused, but I wanted hopefully this is something that's kind of given the situation that can get the information out to you guys in some way. So hopefully the internet will be stable for the rest of the semester and we can kind of keep our normal lecture time. Okay. And so with that, I want to wish you guys a good weekend. Please stay safe. Please stay healthy. Take care of yourselves. Take care of your loved ones. And I'll see you guys on Monday. Sure. What's up? Sure. Mm-hmm. Mm-hmm.